For multiple continuous random variables, we're going to take the same strategy that we did for discrete. We're going to try to extend as many of the definitions as we can from single variable consideration. So the first thing that happens is that we have to define what's called a joint density function, a joint PDF, and that's going to be labeled by f of x and y. Now, when it comes time to working with it, we'll just use the lowercase letters f of x and y. The first requirement of this density function is that it integrates to 1. Now, this requires what's known as a double integral. Now, this is something that is taught in multivariable calculus. Because the density function is a function of multiple variables, you need to know how to integrate with respect to multiple variables. Now, in multivariable calculus, you learn about something called Fubini's theorem. It essentially says that the order in which you integrate these functions is irrelevant, provided that your function is continuous and nice. And it also says that you can do it one variable at a time. So the order is unimportant, and you can do one at a time. If we want to calculate probabilities, so the probability that, for example, x will be between a and b, and y will be between c and d, we would then have to integrate our density accordingly. Now, in this case, it is important to make sure that the limits of integration match with the variable. So the first, or the inner integral, is related to the inner differential just to identify what's what, and these limits have to match with this outer differential. So in an effort to try to show these things to you, I'm going to work on the example that's on the PDF sheet to do with the chemical concentration. Again, some of you may not understand or have worked with multivariable functions before, and so some of this needs a little bit of an introduction. So for example, in part A, we need to determine the value of the constant that makes this integral 0 to 5 f of x and y dx dy equal to 1. Now we've been given that density function is a 20 minus x minus 2y. And because the limits of integration here are the same, it does not really matter which we choose. So we need this to be equal to 1. So at this stage, you can choose. Fubini's theorem says if the function you're dealing with is nice and continuous, which ours is, you can choose any of the variables to integrate first, and the order doesn't matter. So I'm going to start by integrating with x. So your variable here will be x, and you can think of anything that has a y as a constant. So this outer integral remains put. We don't care about it. The inner integral gets evaluated first. The a is a constant, so it can be taken out of the inner integral. And then we find the antiderivative of the stuff on the inside. So 20 minus 2y, each of these is a constant with respect to x. So the antiderivative of a constant just gives you an x, while the antiderivative of x gives you x squared over 2. And this gets evaluated from 0 to 5. Afterward, we will still need that to be integrated with respect to y. So at the end of the first stage of integration here, you should be left with an answer that no longer has x in it. It should only have constants and y's. So we'll have 5 times 20 minus 2y minus 25 over 2. Subtract a 0, because when we put the lower limit of integration in, that will go to 0. So we could clean this up a little bit further. We'll have an a that multiplies 100. To clean this up a bit, a that multiplies 100 minus 25 over 2 minus 10y. And that all gets integrated with respect to y. Now we perform the integration with respect to y. So we'll get our constant a popping out. 100 is the same as 200 over 2. This is the same as 175 over 2. And because this is a constant, when we anti-differentiate it, we'll get a y minus 10y squared over 2. This will all be evaluated from 0 to 5. So we'll have a 175 times 5 over 2 minus 5, because the 10 and the 2 will just give us a 5, times 5 squared. So we're going to end up, after you do the simplification and all, you're going to end up with 625 over 2a has to be equal to 1. And so that tells us that a is going to have to be 2 over 625. And that means then, to properly be a density, this function should have a constant of 2 over 625 into the rest of the portions. Now, if we wanted to calculate the other probabilities, so for example, in part B, if we wanted to calculate this probability, we'd have to set up our integral correctly. This time the limits of integration are different, so you have to pay a little bit of attention to which variable corresponds to which limits. So I've chosen to write the y variable here first. I'll get a dy. I've chosen to write the x variable there. And so this integral, I have to use the value of a that I found above, but now I can proceed as I did before. Now, I happen to put the y variable first. You can swap the order as long as you swap the order of the integration. At the end of the day, you should take this as an opportunity and show that you end up with 27 over 625. So each of these examples gives us basic practice with the tool that we need. And the tool that we need here is multivariable integration. It's more involved simply because there's another letter, but it isn't horribly complicated. And rest assured, we'll only be dealing with problems that are easily integrated. The real tool that we do need, however, is a marginal distribution. And this is just like in the discrete variable case. We're going to hold one variable fixed, and then we are going to sum up over the other. Now, because we are talking about continuous random variables, which typically have an uncountable number of outcomes, sum up is going to be synonymous with integrate. And so we are going to define the marginal densities like this. The marginal density for x, and this is the strange notation, f with a subscript capital X of x, is going to be the result of you integrating the joint density with respect to y. So you're going to be getting rid of all the y dependence. And similarly, you could compute the joint or the marginal density for the y variable. And this is what you would get if you were to integrate the full joint density with respect to x. So above here, you'd be getting rid of all the y's. And in this situation, you'd be getting rid of all the x's. Once we've got the marginal densities or the marginal distributions, you can use them to compute the following. You could use them to compute, for instance, the expectation of x. This has a similar definition to what we did before. We would be integrating x, but this time we integrate it against the marginal distribution. And it would be similar for the expectation of y. Everything would just be replaced with the y variable. We could determine the variance of x by doing a similar thing. Sorry. We would take our previous definition, e of x squared minus the expectation all squared. So we would be integrating x squared times this x marginal distribution minus the result that we got above squared. And you would do a similar thing for the variance of y. And the real importance behind all of this is that x and y are going to be independent if the joint density is equal to the product of these marginal densities. So I realize that I've bombarded you with all of this kind of stuff. So just to try to put it into context a little bit better, in the context of this concentration example, the x marginal density is going to be the result that I get when I integrate the full joint density for our problem. I get rid of all the y's, so I integrate over all the possible y outcomes. So I'll get an integral 0 to 5, and I'll have to put in the full joint density. And I integrate over all the y's. So this is very similar to what was done earlier. But if you were to follow the same steps, you would end up with the following result. You'd end up with a 2 over 125 15 minus x. So this is something that you should verify on your own. Once you have this joint density, you can compute the expectation, and now you would be taking that joint density, or sorry, the marginal density, and now integrating it over x. So we would have an integral 0 to 5, because the limits of x are 0 to 5 here as well. And we would take the result that we just got and integrate over x. Because this is effectively a single variable integral, it's just like what you ended up doing in Calc 2. So you'd integrate through all of those. And going through and hammering out this result would get you to 7/3. So again, I would encourage you to go through, integrate that. The variance would be the result that you would get by taking this difference. So the work that's involved here is you would now integrate this first term in a very similar way to what you did above. You would perform a single variable integral, just like you do. I will leave it to you to practice that. And at the end of the day, you end up with a result of 135 over 18. Subtract 98 over 18, which is what you would get from here, getting you 37 over 18. Now, the part of your pre-lecture is going to be to compute the marginal distribution for y, the expectation for y, and the variance for y. And once you've got those, you would check their independence. And to check their independence, you would multiply together the marginal distributions for x and for y and show whether or not they were equal to the full joint density. And it turns out to be false for this example. They are not equal.